So I'll show through this. Okay. So in the last class, I started with the introduction about thermodynamics, what the subject deals, and as I said, it is the science of energy. Okay. And the thermodynamics, it is a word that comes from actually in those earlier days, we were looking for getting some useful work done through heat. Okay. Why that heat energy in what way we can use like that. So those early efforts were all here for conversion of heat to power. So that is why through Greek words the thermodynamics word came into existence. Okay, and after that the thermodynamics, it is the entire study deals with energy conversion only. We are trying to convert one form of energy to the other form. Okay, so whether if it is heat, then we are trying to convert it to power energy, or if we want a colder if we are doing some work and trying to bring down the temperature, then we are looking for refrigeration applications, or maybe even our thermometer works with the principles of thermodynamics. Okay, there are wide applications, so everywhere we see that. So even in fluid modeling also we need these thermodynamic equations to be used. So that is why the subject is the foundation for any for fluid mechanics or any subject. Okay, so that is why this is very important. Okay, and we have seen that we can convert energy. The only way we can do is convert the energy can be converted to one form to the other. So you cannot create energy or destroy it. Okay, so you have to gain bring some energy from the other source. Okay, so that with these three examples we had some look, and we tried to have some discussion on these three examples. And apart from that, what way these thermodynamics can be studied? There are two ways. One is classical thermodynamics, and the other one is statistical thermodynamics. The statistical thermodynamics, it deals with independent molecules. You have to look at each and individual molecule, and or else a set of molecules. Through those behavior, we can study thermodynamics. But the classical thermodynamics deals with the whole system. It takes the entire system into consideration, and we are trying to get the we are trying to study the behavior of heat. Okay, so we have two methods. One is microscopic and macroscopic. Obviously these words itself, they say if you are looking at molecular level, then that is a microscopic, and if you are looking at a as a system as a whole, then we that is called macroscopic. Okay, so we are completely dealing with only classical thermodynamics. We are not dealing with any other. Okay, so we deal with only classical thermodynamics in this subject. Statistical thermodynamics, they will be dealt by chemical engineers or anyone who are trying to look at the atomic level. Okay, whether it is a nuclear scientist or any chemical engineers, they will be looking at statistical thermodynamics. Okay, so in macroscopic approach, for each individual particle, you can get xi, that is position, velocity, and mass. Okay, and in macroscopic world, obviously we can get pressure, volume, and temperature. Okay, so in macroscopic, the best example that you can get is tire pressure. The measuring of tire pressure is the macroscopic um, reading, or else body temperature if you take. So temperature is also a macroscopic approach. You can measure any property of a system, or else you can look at volume also. Volume is as a system together. And here in microscopic, obviously we are looking at individual particles. So one example is property of atoms. Okay, if you are a nuclear scientist, we are looking at the fission process and all, or if it is if or else a fusion process. Okay, so mostly in nuclear physics we are dealing with the fission process, right? So uranium. So that was about. Then we had a look at what are the applications of thermodynamics, and after that we saw what is a system. So what is a system, and what is the surroundings? If you consider any system as a whole, so and outside the system, it is called surroundings, and with the membrane that is or a separation region that is separating both system and surrounding is the boundary. Okay, and after that we saw what are the types of systems. We have control mass system and we have control volume system. Under control mass system, if you are controlling a mass, that means there is no mass change. Okay, there is no mass change. So m dot is equal to 0. Okay, dot means dou m by dou t. Okay, so change of mass with respect to time, if it is 0, then the system is control mass system. Under control mass, we have closed system, isolated system. These are the major three classes, but they come under subcategories. Okay, so control mass, control volume. In closed and isolated, we have sorry, M10 this. In closed system, you don't have no mass transfer, only energy in, energy out. In open system, you have energy mass in, mass out, energy in, energy out. In isolated, you have no energy transfer or no mass transfer. The best examples we have seen as a closed container, if you have some gas inside and you are heating the container, then you can see that the mass initially it was 2 kg and the volume was 1 meter cube. But later, after some time, you see that after heating, the gas expands, right? Thermal expansion will happen. Because of thermal expansion, the mass although will remain the same, but only volume will change. Okay, so this is a closed system where only the mass, there is no mass change at all, no mass transfer. Okay, only energy transfer will be there outside to inside. And in control volume, you can take the best example as nozzle, or you can take our motor vehicles, IC engines where you are bringing in some fuel, burning it, and then you are taking out the, but the volume inside this system will be the same. Okay, it won't change, right? So it keeps, it will never change. So that is why you have control volume where you are fixing the volume, but there is mass in and energy in both. Okay, energy in and out will be there, mass in, mass and mass out will be there. Okay, so this was about control volume. Then we had to look at what is a property of a system. Property, you can say that it is a measurable characteristics of a system. Okay, so best example is pressure, temperature, volume and mass. Okay, these four are basic ones through which these properties can be, these are the properties that define a system, what is the characteristics of the system. Okay, then you have in thermodynamic properties, you have two categories where one is intensive and one is extensive. Intensive is, if say you are taking a container and you have temperature, pressure and density or volume and mass, the same container if you are cutting into half, then the temperature, pressure and density won't change because they don't depend on the total mass of the system. Rather, mass and volume, they depend on the mass of the system. So if something is dependent, some property is different depending on the mass, then that is an extensive property. So if the properties are not depending on the mass, then they are intensive properties. That means pressure, temperature and density, they are all intensive. Mass, volume, obviously if you are cutting down this into two halves, the entire tank, then mass will change, volume will change, energy will change, enthalpy will change. Because there are energy, you know that if say you are taking kinetic energy, then it is half mv square, right? So they are depend on mass. Okay. Then state and equilibrium. What is a state? Okay, state is a at one particular stage, let's say at equal to time equal to 3 p.m. Okay, at time equal to 3 p.m. what is the state of that? Okay, if you look at temperature, volume, then what is the state of that system? Okay, at the same system, if you are looking at t equal to 12 p.m. Okay, if you are not 12 p.m. Let's take some 7 p.m. Okay, if you are looking at the same properties at 7 p.m., if it is changing or not changing, if you are looking at different time, then that is the different state. Okay, so that is the state of a system. Okay, so the properties that describe the condition of a system at that particular time. At 7 o'clock, what is the conditions that would describe the properties of the system? Okay, so that is called the state. And equilibrium, the word equilibrium itself will say that it implies the state of balance. Okay, it implies the state of balance. If you say you take a container and you have different, within the container, if at different locations you have different temperatures, then obviously if you leave it for some time, obviously the entire container will come to an equilibrium state where there will be no change in properties inside. Okay, so that is what is this is thermal equilibrium. Okay, this is thermal equilibrium. This is the example of thermal equilibrium. Okay, a very simple example, because so if you take the hot cup of coffee, a hot cup of coffee, if it was at 70 degrees centigrade and the outside temperature was 20 degree, then obviously both of them, the heat will, if you didn't touch the container at all and you closed it with a small lid, then After some time, the container, the heat energy will start flowing from hot to cold, and after that, at some two after 2 hours or 3 hours, both of them they come into an equilibrium where there is no heat transfer. Okay, so this is the example for thermal equilibrium. Okay, so after that, let's start looking at the types of equilibrium. So today we'll start with types of equilibrium. Okay, let me take a new whiteboard. Yeah. Okay, so we'll start with types of thermodynamic equilibrium. What are the types of thermodynamic equilibrium? Okay, so as I said, equilibrium you have equilibrium is what? It is a state of balance. Okay, state of balance. So you are reaching a balance in the system. Okay, so within that we have different subcategories. Okay, let me take this. Within this you have different subcategories. Let me draw a line here. Okay, so here first thing that we see is thermal equilibrium. Thermal equilibrium. Okay, so here in thermal equilibrium there will be no temperature gradient. Okay, there will be no temperature gradient. No temperature gradient. The best example that already I have shown. Let me put it here as well. Okay, so we'll keep it here. No thermodynamic equilibrium, or we can write, or temperature is temperature gradient is dou rho by dou x, dou t by dou x. Okay, so what this mathematical word dou t by dou x is, at different positions there is the change in dou t by dou x will be equal to 0. Okay, that is what is temperature gradient is 0. Okay, spatial gradient. So you can ignore that. Now in terms of simple English, you can write it is same throughout the system. Is same throughout the system, with space as well as with time. That means in mathematical term you can call dou t by dt. Small t is time. This also is 0, and dou t by dou x. This also is 0. Okay. So the example that I have already showed, right? So let me put it again back that. Yeah. Yeah. So this I have already showed, right? Yeah, let me put it here. Uh, okay. So this was at some particular time where you had different temperature distributions, and after some time they come onto at each every location you have the same temperature. Okay, so this is what is dou t by dou x is equal to 0. That means at any point if you take derivative there, then it will be 0 there. Okay, so that is thermal equilibrium. So the first thing is I put an underline there. Then after that we have mechanical equilibrium. Mechanical equilibrium is the word mechanical means motion, right? So if you say you have a tank, let me take whether I have figure. Yeah. Yes. No. Let me take another one. Yeah. Let's say you have a system like this. Can ignore this. Please ignore this one. Okay. Okay. Let's ignore this. Let's say you had some pressure here, P1, and outside ambient pressure was something like P2. So let's assume that okay, there is this pressure here is very far greater than, I'll put double greater, okay, double or triple greater, very high pressure than P2. Obviously, what happens? This internal pressure, because P2 is very low compared to P1, P1 is very high, right? So because of this, the pressure difference will try to push it in the upward direction, right? So that is what is a mechanical motion, right? So this is mechanical motion because of pressure. Okay, so there should be no here because of because due to this pressure difference you will have the motion. Okay, so let's say this P1 and P2 is coming to equilibrium after some time. Okay, let's say this cylinder is a bit further, and obviously after some time this piston will move until P1 is equal to P2, right? So that is after that, so till it comes to P1 equal to P2, then this piston will move and it will stop somewhere here, right? So once it is stopping, so that is what is, we can call it as mechanical equilibrium state. Okay, or else you can take this way. Let's take a container, same thing, and you take a same container like this. Okay, and say you have here one pressure like 2 psi, or here take some 5 psi. At different points you had different pressures. Let's say here some 6 psi, and here you have some 10 psi. Okay, so pounds per square inch. Okay, psi is pounds per square inch. Okay, so after some time, because of this difference in pressure, what happens, they'll all try to mix up, and they'll come to some state where everywhere you will see that there is some maybe some 6 psi pressure or something like that. Okay, everywhere you'll see that there is 6 psi. So here the same thing, thermal equilibrium, here no pressure gradient should be there. No pressure gradient. Same thing as thermal equilibrium, but here we have no pressure equilibrium, no pressure gradient, or pressure is same throughout the system. That too with time. Okay, so that was mechanical equilibrium, and after that we have uh, okay. So after this we have chemical equilibrium. Chemical equilibrium. Same thing. The word itself will say there is no chemical reaction, right? So once after some time you're first you are mixing two different chemicals. Once the chemical composition, if the chemical the reaction will start, right? After the reaction has started, it will try to produce a new compound. Once the new compound is coming, uh, is, is produced, then obviously the system will try to balance itself, right? So there will be, the chemical composition will become constant throughout the system. Okay, like this, the same here we saw pressure, there on the top, in the first case we saw temperature. Now here chemical composition will be uniform throughout the system. Chemical composition is constant everywhere. Chemical composition is constant. And after that, no, also no reaction occurs. We'll see there is no reaction occurring at all. Okay. So after that we have the fourth one, final one, phase equilibrium. Phase equilibrium, the word phase, you have to know what it is phase. Okay. Let's say you have two different fluids. Okay. Let me take a container where here it is a closed container. In this half, I am filling it with water. Let's say on top I have here you have let's say there are two different gases. Okay, here you have N2 and here you have O2. Okay, so you have taken half of that section and mix it with half with O2 and then the other half with N2. Okay, so no, both of them are gas. Sorry. So let me take. Okay, let's take liquid O2. Okay, this is in liquid form, liquid O2, and the other way you are having gas O2. Okay, so this is gas, or let's say CO2. Okay, here you have CO2 and here you have liquid O2. Obviously, both of them they'll try to mix up, right? Two different, or just like mixing an oil and water. Okay, so both of them they have different phases. Okay, so this is in gas phase and this is in liquid phase. Okay, so once they're mixed together, then we see that system after mixing together they'll try to become only a single phase. Okay, if you have two different phases like two different mixture, or let's take as a IC engine where you have in the inlet, what you do, you don't inject only fuel, right? You don't inject only petrol, you'll be injecting the general air also, right? Or let's say O2. Then only once you use a spark plug and you burn them, so inside the cylinder you will see that the combustion starts. Okay, so although we are sending liquid and gas inside, both of them, the ones we are burning them, they are becoming into a single phase and they are moving out, right? So that is what is phase equilibrium. Two different materials, if they are mixed together, they will obviously try to reach into an equilibrium, that is phase equilibrium. They become into a single phase. Okay, system having more than one phase. Okay, they try to reach equilibrium there. Okay, more than one phase. Okay, so this is about three types of equilibrium that we have. Four different types of equilibrium. The first three are very important. Okay, so mostly because since we are not dealing with multi-phase, we will be looking at this very less. Okay, so thermal equilibrium, mechanical equilibrium, and chemical equilibrium. These things are very widely used in our applications. Okay, so this was about thermodynamic equilibrium, and first thing that you should know is what is equilibrium. It is a state of balance. Okay, and after that, what are the types of equilibriums? Okay, so proceeding further, let me take another one. Okay, so what is a state postulate? Okay, here we see something called state postulate. A state postulate. Okay, a state postulate is something. Just say you want to define some system. Okay, let's take this nitrogen cylinder. Okay, let's take this nitrogen cylinder. Okay, so this particular, as I said, state is something that defines the characteristics of the system, right? The state was definition of state was the properties that describe the property that describe the condition. Um, that property that describe the conditions of the system. Okay, the condition of the system. Okay, so that was state. Okay, a state postulate is something in order to describe this system state. Okay, in order to describe this state of the system, what are the number of properties that are required to be described? Okay, so in putting in words, a state postulate is the number of properties, the number of properties to required to fix the state of a system. The number of properties that you use to describe the state of this particular system, then that is called a state postulate. Okay, is state postulate. This is very important. This is very much stressed because uh, each each and every system will have its own different requirement. If this is a single phase flow, in single phase you are having only one N2, right? So because of that, you can say that, okay, with these two properties I can explain, okay, what is the state of the system. Let's say you have number of proper compositions, N2, O2, or even liquid H2O, or even petrol, some hydrocarbon material is there inside. So all these things, let's say four phases are there inside, four different gases are inside, or two gases and two liquids are there inside. Okay, so how many properties are required to describe that state of the system? So that is what is a state postulate. Okay, so that is why it is separately defined. Okay, so here we are taking a small cylinder with a single gas only. Okay, with that there we can assume that, okay, you have a single phase. So if you have a phase one, okay, then you can describe it with two properties. Okay, for this system with two properties you can describe its state. So that is what is a state postulate. Okay, so mostly two intensive properties are enough to describe any particular system. Okay, so here that is why we are using two intensive properties there. Okay, going by next, then okay, so let's talk something about process. What is a process? Okay, so any IC engine operation that is going on, you have to define it as a process. Okay, what is going on? First, there is something called, intuitively you know that there is fuel injection that is going on. After that, you are burning it. Then the piston moves upward. Then the burnt gas is removed outside, and after that, again the new fuel is taken inside, and then again burn, and then the piston moves up and the burnt gases will go out, like, so that is a cycle process. Okay, so that graphically and as well as mathematically you have to define what that is. Okay, so that is what is a process there. In thermodynamics we look at each and everything as a process. Okay, so you'll be dealing most of this every time. Okay, in the entire subject you will be looking at what is the different types of processes that are we are dealing. Okay, so first we'll define what is a process. So let me take a simple example first and I'll start it. Okay, let me start with this. Okay, so assume that this is the same cylinder like what I have showed here. Okay, this in the earlier figure I have showed, right? Yeah, take it out. Yeah. Okay, so this is the same cylinder at different state. Earlier this is the initial state. Okay, so this is the initial. Let me delete this. I just wanted to show you. Let me delete this. Okay, so here this is the initial position. This is the initial position where this piston was here. So when the piston was here, that is what is the initial position there. Obviously, we are trying to define this process with two terms. One is pressure here. Okay, this is pressure, and here the V here is volume. Okay, so on x-axis I am having volume, on y-axis I am having pressure there. Okay, so now if you look at this cylinder, uh, this is the initial position of this piston. We are trying to move it slowly, okay, at different positions. First, initially, after that, let's say after some time, the location of the piston was here somewhere, okay, and then after some time the piston was somewhere here, then after that the piston was somewhere here. At different locations like this, obviously we know that when the piston is somewhere here, so when the piston is here, this is the entire volume, right? This is the entire volume. Let me delete this first. When the piston is here, this is the entire volume. This is the system boundary, and you have pressure as P and V there. So if you mark this with respect to P and V, this is the point, first point. After that, let's say you're moving your piston somewhere here. Okay. So at this location, the boundary has reduced, right? So volume is obviously reduced. Okay. So this is now new P and V. Okay. So if you plot this at this location, so let me put a marker there. Okay. And this is my new P and V. And like this, I keep moving my piston. If the new piston is right now here, then obviously the pressure will be higher and volume will be lower. So then that is why you'll see another point where here, let me take this, that is becoming very difficult. Yeah. Okay. So let me delete all this stuff. Let's bring this, yeah. When this was here, so this is my reading, right? So this was my reading. Then at another time, I have moved my piston here. So the piston face is here. Then obviously the new volume, the point will be somewhere here. Okay. So if you are making this chart and taking this series of points, so this is my process path. Okay. So here again we have moved somewhere here. The piston has moved somewhere here, and so this is my new point. Okay, like this, if we create the number of points like this, what is the new values when we are slowly moving the piston one by one, one by one, one by one. So new pressure and new volume will be, we will be getting new values, right? So once we are making this locus of this point, this line or the curve, the locus of these points, it is the process path. Okay, or that is a process that is going on. Okay, so that is it. Intuitively here, this is what, if you are trying to describe some process, what happened. So from initial state 1 to final state, this is my final position. Okay, so this is my final position. At this point we had this much pressure and volume. So what are the properties that describe this line, the way it is moving? So that will describe the process path, how the process has moved. Okay, so right now I should not be telling you, but still, why this plot is needed, that I'll tell you. The reason why you make this pressure and volume plot is, with this, the area covered within this plot is there, right? So with this plot you can measure how much work has been done. Okay, the area under this curve will give you work done. So that is why this is very widely used in thermodynamics. Okay, so that is why this process, you have to know what is this process. Okay, or the process path, what is the important, how you make these plots and all. Okay, so the area under this curve, if you are taking PV diagram and if you are trying to measure this, what is the area under this curve, then you get how much work you have done, okay, in terms of joules. Okay, so they are very useful in thermodynamics. Okay, so that is why every process they try to give it based on this PV diagrams. Okay, so let's start. Let's first describe what is process. Okay, I have given the use. What is the purpose of this? Okay, let me move this. Diagram. This is not moving. Okay. Okay. So let's start with the definition. How you can define the process. Okay. When you're defining a process at a basic level, you should say that okay, this is property A and property B. It can be anything. Okay. Here I have showed it as a PV diagram, but it can be anything. Okay. First, I'll say write the definition. Any change that a system undergoes from one equilibrium to one equilibrium state to another. Why I'm using the word equilibrium is here I said that we are slowly moving it, right? Slowly moving because the equilibrium state should be there. That means there should be no disturbance to the other surroundings. Okay, there. If you are moving it very fast, what happens? Intuitively, you know that there is some friction force that is going on, right? Because of that friction force, you are emitting some heat. Okay, some heat energy will be. So you are disturbing the surrounding. Without disturbing the surrounding, slowly you have to do this process. And after that, once you are get bringing this once it has moved to the final state, and if you are moving the piston backward slowly, one by slowly, very slowly, then you should get the same path. Okay, so that is why this undergoes from one equilibrium. That is why we use from one equilibrium state to another is called a process. Okay, so it's called a process. The series of states through which the system passes. So this is path, right? As I said. So process is from one state to another. If it is changing, then that process that is called a process. Okay. And after that, the series of states. If you are clubbing together all the series of states through which the system passes, passes during a process is called path of the process. Is called path of the process. Okay. So here we get two different definitions there. Okay. So it can be any, as I said, this plot can be anything like this. Let me bring out another one. Okay, so let me put it here. Okay, so if you can take for a system, you can take any two properties. It can be P or it can be T or it can be density or anything. Okay, and here you can take volume or you can if say you can draw PV diagram. This is PV diagram. Okay, pressure volume. You can draw TV diagram. You can draw TS diagram. Yes, let's not use the S word now. I'll teach you later. Okay. So TV diagram, any property you can bring in and you can draw the process what is going on. Okay. So it doesn't mean that you have to. So with what under this plot, let's say you are drawing TV diagram, then the path under this curve will have its own importance. Okay. So as I said here in PV diagram, this region will give you the amount of work done that was have that is required to get this process done. Okay, so in the same way here TV also will have its own purpose. Okay, so one by one we'll learn it when you are trying to design any IC engine cycle or anything. So you will be able to explain it through this process path. Okay, So there are cycle paths also where you have some for IC engines we have Carnot cycle. So for the jet engines they have Breton cycle like that. So there are different cycles for that. So we'll learn some of those cycles here. Okay. So that was about process. Then we have something called quasi equilibrium process. Okay, this process again we have some lot of subdivisional processes where you have different reversible process, irreversible process. Then we have adiabatic process. You will be listening to these processes, number types of processes, isothermal process. Okay, one by one we'll start looking at. So let's start with quasi equilibrium process. Okay, so let me take a new board. Okay, let me start with quasi equilibrium process. Quasi equilibrium. Quasi equilibrium because this will simplify our calculations. Okay, so if you are assuming that the process is going on smoothly in this cylinder itself. Okay, so let's assume. Let me take the cylinder where you have some compression going on, right? Slow compression. Let's assume that you are doing some slow compression. Okay, in this direction you are moving, right? Here the arrow is there. So in this, if you are doing slowly the compression process, if you are doing it very slowly, then you will be looking at, you will be concentrating only about the pressure change or volume change or temperature change here. You are not required to look at any what is happening at this at this junction. Okay, intuitively if you know here there is friction process that is going on, right? In real world you will have friction. If say you are slowly moving it, then there will be no contribution from friction. That will be very marginal. You can ignore that losses because of that friction. If you are doing fast compression, then the friction also should be considered. So you have to, if you are doing some mathematical calculation, mathematical modeling, at that time you have to simplify your number of variables. You should be taking very less number of variables as much as possible. Okay, in order to avoid this friction effects of the effects due to friction and all, once there is a friction, there will be some heat addition, right? So all those things, if you want to ignore it, then you should consider that every system is a quasi equilibrium process. Okay, quasi equilibrium means let me put up this. Yeah. Okay, let's say, yeah, I'll delete these things. It's not needed. So let's assume that this is the slow compression process. Slow compression. Compression, I know, you know, right? The word compression. Okay, we are compressing the gas inside. Okay, assume that it is very slow, very, very slow. You are moving it very, very slowly. So when you do that, when you're considering something like a process like this, so first thing, so anyway, instead of typing it, I'll put this up. Let me put this here. Okay. So when a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium. I think you are able to see this. Let me zoom out. Okay. So when a system proceeds in such a manner that the system remains infinitesimally small close to an equilibrium state. Okay. If you are the process is proceeding in such a manner that it is close to equilibrium state at all times, it is quasi-static or quasi-equilibrium process. Okay, if you are moving it close slowly, then the process is in quasi-equilibrium or quasi-static process. So quasi-equilibrium can be viewed as sufficiently slow process that allows the system to adjust itself, okay, internally, so that properties in one part of the system do not change any faster than the other parts. Okay. So here, if say you are doing some sudden compression, okay, like this. Let's say you have suddenly moved it this far. Okay, let me paste it here. Instead of moving it slowly, in the same time, here you have moved it this far. So what happens? You can assume that there is, let's say, suddenly you have moved. So what happens? Because at this position, let's say at this region there will be very high pressure within this, and here you will have different pressure, and it might take some time to get into equilibrium, right? So if you are slowly moving this, then the P1 will be everywhere same if in quasi-equilibrium process. Okay. If you are suddenly moving very fast at the same time, this is also at t equal to 1 second, and this is also at t equal to 1 second. Suddenly, if you have moved, there will be lot of pressure accumulation, and there will be density change also will be there, and there will be some marginal temperature change also when compared to the other regions. Okay, other regions will have see different pressure. Okay, so that means this system, when you are moving it fast, it is not under mechanical equilibrium, right? And at the same time, it may not be under thermal equilibrium also. So that is why what happens is that here, that is what is written. A quasi-equilibrium process can be viewed as a sufficiently slow process that allows the system to adjust itself internally so that the properties in one part of the system do not change. One part of the system do not change. Okay, so the property should not change anywhere rapidly. It should be uniform. That means it should be under thermal equilibrium also, and it should be under mechanical equilibrium also. Both of them should be there. Okay, so that is what this is a slow compression process, and this is fast compression. Okay. So fast compression process, this is non-equilibrium process. Okay, this is a non-equilibrium process. Non-equilibrium. But in real world, this is a equilibrium process or quasi. The reason why we use quasi is quasi means near. Quasi word is, the English word quasi means close to or near, near to. So it will be near to the equilibrium process. Okay, because 100% equilibrium is not possible, right? Because there will be some thermal friction forces, or there may be some other effects. There may be some leakage of gas from this. Because of that, there will be some pressure loss. Okay, so assuming that people have made it as quasi equilibrium, that is close to equilibrium process. Okay, 100% equilibrium is not, does not exist at all. Okay, in order to simplify our calculations, we are trying to take it as a quasi equilibrium process. Okay, engineers, we as an engineers, we are interested in quasi equilibrium process for two reasons. Okay, for two reasons we are first, they are easy to analyze. Okay, you know, you don't have to consider into different you don't have to bring all the different effects of friction or heat addition, or even if there is any leakage of gas, you don't have to worry about those things. The number of parameters required to test this system will be less. Okay, you will be worried only about pressure and volume and temperature. Okay, the number of parameters will be less. So first, easy to analyze, and second, work producing devices deliver the most work when they operate at quasi equilibrium. Every engineer's target is to design his system in such a way that that is close to quasi equilibrium. He'll set this as a target. Okay, his system should be near to quasi equilibrium. If it is an IC engine, or if it is a jet engine, or any mechanical operation devices or thermal operation devices, then everyone will try to design his process in such a way that it is close to quasi equilibrium, because the work producing deliver the most work. Okay, work producing devices will produce the most work. So that is why we look at engineer's target will be to design it close to equilibrium. Okay, so after that, therefore quasi-equilibrium process serve as a standards for which actual processes can be compared. If you have designed a system and then you have created the process, the quasi-equilibrium is the standard. Okay, it is a standard benchmark for you. Okay, it should be close to the main system. Okay, so with this quasi and non-quasi equilibrium process, the processes that are not quasi-equilibrium, they are non-quasi equilibrium process. Okay, so with this we'll non-quasi, not quasi, non-equilibrium, non-quasi equilibrium process. Okay. So with this, we'll close today's session. Okay. Let me save your attendance sheet. Also, today's strength is very low, 16. Okay. Anyway, any doubts? I'll leave 5 minutes. Okay. Any doubts up to here, guys? Hello. Hello. Hello.
No, sir.
Lokesh Reddy. Or so in the next class we'll see the further things. Lokesh Reddy, you're asking something?
Nothing, sir.
Nothing. If you have any issues, you can post it in the post section. Okay, in the channel, in our channel. Okay,
Okay.
in engineering thermodynamics channel, you just drop some queries. Okay, in the next class when I start, I'll start by answering those things, and after that I'll continue the class. Okay. So any issues, please
Yes.
contact me, or you can post it in the channels group. Okay, you can discuss it, or else through chat you can send me a personal message also. Okay, there is a main in Teams, you have main section chat, right? So in that you can also send some